In this video, I will show you how to create the famous simulation called Conway's Game of Life. It is by far the most interesting project we have built in this channel so far. It is a project that blows my mind. Here is a quick overview of what Conway's Game of Life is all about. It is a cellular automaton devised by the British mathematician John Conway in 1970. The game is a zero-plate game, meaning that its evolution is determined by its initial state, requiring no further input from human players. One interacts with the game of life by creating an initial configuration and observing how it evolves. Conway's game of life might seem super simple because it has just a few rules, but here's the cool part. Even with those simple rules, you can see all sorts of amazing patterns pop up. It is like magic how a bunch of squares on a screen can start doing things that look almost like they are alive. You've got patterns that don't move at all, called still lifes. Then there are oscillators, which are like the heartbeat of the game, flipping back and forth in a rhythm. And there is even more wild stuff like spaceships, which travel across the screen, as if they are exploring space. What's really wild is that with just these basic bits and pieces, you could, in theory, build a computer inside the game. That's right, those blinking squares can do anything a computer can do, just by turning them on and off according to the rules. So even though the rules are easy to understand, the game of life shows us something awesome. Simple stuff can come together to do really complex and unexpected things. The game of life is a fun way to see how complexity can come out of simplicity and gets you thinking about the big picture of how the world works. In this tutorial, we will walk through building a simple version of Conway's Game of Life in Python using Pygame, a popular set of Python modules designed for writing video games. This will include setting up our environment, creating a grid to represent our world, applying the rules of the game, and adding controls to pause, reset, or change the state of our game. So let's start at once. Game of Life may seem complex and challenging to develop, but fear not. We will take a divide and conquer approach to make it more manageable. In this tutorial, we will break the development process down into 7 steps, tackling each one individually and building upon what we have accomplished in previous steps. With this approach, you will be well on your way to creating your own version of Game of Life in no time. So, let's get started and see how we can conquer this challenging project one step at a time. The first step is to install Pygame. Pygame is a Python library used to create games and multimedia applications. In this tutorial, we will be using the Pygame Community Edition, a fork of the original Pygame library that is updated constantly with new features and bug fixes, and it is faster than the original Pygame library. In Game of Life, speed can be an issue in large simulations, so pygame-ce gives us a speed advantage. However, you can also use the standard Pygame library if you prefer, as the code we will be using is exactly the same. To install the pygame-ce library, all we have to do is to open a terminal window and type the following command: pip install pygame-ce. With the Pygame library installed, we can now verify that it is working correctly by running a simple test script. To do this, we create a new folder. Let's call it Game of Life. And then we create a new Python file in it and we name it main.py. Now we can open this file with our favorite editor. I will be using Sublime Text in this tutorial. Inside the file we have to import Pygame by typing import Pygame. Next we have to run the program to see if Pygame is installed correctly. In Sublime Text, simply press Ctrl+B to run the program. If you see the message pygame-ce, our installation is working fine and we have successfully completed step number 1. That was easy, wasn't it? The next step in building our Game of Life simulation is to create a blank screen and set up the simulation loop. Before we start, it is important to understand the structure of today's simulation. It consists of 2 parts. The first part of the simulation is where we define our variables and our simulation objects, such as the grid. The second part is the simulation loop, which is responsible for updating all the cells of the grid and then displaying the grid. The simulation loop is like the heartbeat of the simulation, running repeatedly until the simulation is closed. In each iteration of the simulation loop, we will update the grid according to the rules of the simulation, and then we will display the grid. All this will happen so fast that it will appear as a continuous movement. Now let's create a blank screen and the simulation loop. First of all, we need to initialize Pygame, so we type pygame.init. Then we create a display surface. A display surface is like a blank canvas where we can draw our simulation objects. We need to specify the width and the height of the display surface. I am going to use a size of 750 by 750 pixels. Let's create the display surface. First, let's create two variables to hold the screen width and the screen height for our game. Window width is equal to 750 and window height is equal to 750. Now we can create the display surface. Window is equal to pygame.display.setMode parenthesis and again parenthesis window width, window height. This line of code creates a display surface object named window. The setMode method takes a tuple as an argument. The first value is the width and the second value is the height of the display surface, our canvas. In simpler terms, we just created the simulation window, and to draw on it, we use a coordinate system similar to the one taught in high school. Each point on this window has its unique x and y values. The coordinate system used in computer graphics differs from the standard Cartesian coordinate system taught in high school. In computer graphics, the origin of the display is located at the top left corner, with 0, 0 being at the top left. In contrast, the standard Cartesian coordinate system starts from the bottom left corner, with 0, 0 being the origin. In this system, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move up. However, in the top left corner coordinate system used in computer graphics, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move down. This means that a point at 10, 10 will be located 10 units to the right and 10 units down from the origin. We will be using the top left corner coordinate system today. That's why it is important to understand the differences between these two coordinate systems. Now that we have created the window, we need to give it a title. We do that by using the setCaption function. pygame.display.setCaption parenthesis quotes game of life. Next, we create a clock object like this. Clock is equal to pygame.time.clock parenthesis. Be careful, we need a capital C here. We need this clock object to control the frame rate of the simulation, how fast the simulation will run. Don't worry about this line of code now. We will get back to it in a minute. The basic setup of the simulation is now complete. Let's now work on the simulation loop. The simulation loop consists of three parts. First, event handling. First, we need to check for any events that occur in the simulation, such as quitting the simulation, a key pressed on the keyboard, etc. This is done using the Pygame event handling system. Second, updating. Next, we update the state of our grid according to the rules of the simulation. Third, drawing the objects. Finally, we draw all the simulation objects in their new state on the screen. This step uses the Pygame graphics functions to render the objects on the display. Today, we just display the grid. By following these three steps, we can create a dynamic and interactive simulation that responds to the user inputs and updates its state accordingly. Now, let's implement these three steps. Let's write a comment first. Comment here, simulation loop. We start the simulation loop with a while loop like this. While true, colon. The while loop is an essential part of our simulation. It runs continuously until we close the simulation. At each iteration of the loop, we perform three key steps: checking for events, updating the state of the grid, and lastly drawing the grid. Let's place some comments to help us organize our code inside the simulation loop. 1. Event handling goes here. 2. Updating state of the grid goes here. And 3. Drawing the grid goes here. It is important to note that before running the simulation, we need to ensure that the code inside the while loop has been fully written. If we run the code at this point, the while loop will run forever, since we have not defined a way to stop its execution. So in the next step, we will add the necessary code to stop the while loop. For event in pygame.event.get parentheses and a colon. This line of code gets all the events that Pygame recognizes and happened since the last time the while loop ran and puts them in a list. Then we loop through the list of events and check if any of the events is the quit event. The quit event is when we click on the close button of the window. If the event is the quit event, we break out of the while loop. If event.type equals pygame.quit, colon. Pygame.quit, and then we have to close the program completely with the command sys.exit. This command is part of the sys module, so we have to import it like this. In the first line of the code, after importing pygame, we type sys. That's it. Now we have defined a way to exit the game, but we need a couple more lines of code before running our game for the first time. We have to update the screen with this line of code. pygame.display.update. This line of code takes all the changes we made in the simulation objects and draws a picture from them. Since we haven't created any simulation objects yet, this line just draws a black screen. Remember the clock object we created at the beginning? We need to inform the clock object about the maximum speed at which our simulation should run. This is done through the tick method. The tick method requires an integer argument, which represents the maximum number of frames per second we aim to achieve. Typically, games run at 60 frames per second, but for our Conway's Game of Life simulation, we will set it to 12 FPS. This slower refresh rate will help us better appreciate the unfolding simulation without it speeding past too quickly. First, let's define a variable at the top of our script to hold our FPS value. FPS equals 12. Now, inside the game loop, we have to call the tick method of the clock object. Clock.tick parentheses FPS. That's it. This means that the while loop and all the code inside it will run 12 times every second at most. This setup doesn't guarantee that our simulation will run at exactly 12 frames every second. Rather, it sets 12 frames per second as the ceiling. This means our simulation won't run faster than 12 frames per second, but it could run slower, depending on the system's capabilities and the complexity of the scene being rendered. Now that the simulation loop is complete, we can run the simulation for the first time. As you can see, nothing is inside the simulation window because we haven't drawn anything yet. But the important thing is that we can see the game window with the title and the dimensions we defined, and that we can reliably close the simulation by clicking on this X icon here. Beautiful. The simulation window is black. Let's make it a dark gray color. Pygame provides several built-in colors, but we will be defining our own colors today. In Pygame, colors are represented as a tuple of 3 values, each value representing the amount of red, green, and blue in the color. The values for each component range from 0 to 255, where 0 represents the absence of the color and 255 represents the full intensity of the color. For example, to create a red color, we would create a tuple with the following values. Red equals, parentheses, 255, 0, 0. These values represent the red, green, and blue components respectively. So, to create a gray color, we will create a tuple like this. Gray is equal to, parentheses, 29, 29, 29. Now, let's paint the simulation window gray. Inside the simulation loop, before updating the window, we call the fill method of the window object like this. Window.fill, parentheses, gray. The fill method just fills the display surface we have created, our canvas, with the color we define, in this case gray. If we run the simulation now, we can see the simulation window is now gray. Beautiful. We just completed a very basic simulation loop, so we can remove step number 2 from our list. We have made progress. Moving on to step number 3. We are about to create the grid. Before we dive in, let's discuss why a grid is essential for Conway's Game of Life and how we will represent the cells within it. Game of Life unfolds on a two-dimensional board filled with square cells. Each of these cells can be in one of two states, alive or dead. As the game progresses through each generation, each tick of a clock, the cells evolve based on the states of their neighbors. The grid is the backbone of our simulation. It organizes the cells in a structured manner, allowing us to track the state of each cell efficiently and to apply the rules that govern their evolution. It's what makes visualizing the complex, emergent behaviors of the game of life possible, turning simple rules into mesmerizing patterns. For our purposes, the grid also simplifies the programming challenge ahead. We will represent it as a two-dimensional array, where each element corresponds to a cell. To make things even more straightforward, we will use a binary system to represent the state of each cell, 1 for alive cells and 0 for dead cells. This representation allows us to use simple arithmetic to count live neighbors and determine the next state of each cell based on the game's rules. Therefore, in this step, our task is to set up this foundational grid. We will decide on its dimensions based on our window size and the cell size we want. We will then initialize our grid with zeros, representing an initial state where all cells are dead. From there, we will develop functions to draw the grid on our screen, visualizing alive cells distinctly from dead ones, and thereby bringing our simulation to life. Let's begin this exciting journey. Back to our code. First, let's create a grid class. We will do so in a separate file. We can press Ctrl+N to create a new file and then Ctrl+S to save it as grid.py. Now let's start writing our grid class. Class grid : dev init self : Now let's think about how we are going to create the grid. We know the width and the height of the simulation window. It is 750 by 750 pixels. Let's make a grid inside this window containing cells of 25 pixels in width and height. To figure out how many cells we can fit across the width and the height of our window, we divide the window's dimensions by the size of each cell. When we divide 750 by 25, the result is 30. This calculation tells us that both horizontally and vertically we can fit 30 cells. Consequently, our grid will be structured into 30 rows and 30 columns, summing up to a total of 900 cells. So let's go back to the main.py file and add a new variable at the top, named cell size. Cell size equals 25. Now back to the grid.py file. We can press Alt+2 on the keyboard and Sublime Text will display the second open tab of our project. To construct our grid, we need to know the dimensions of the simulation window and the cell size. So let's give the class this information as an input into the init method, width, height, cell size. With this information, we can now calculate how many rows and columns the grid will contain. So let's create two attributes. Self.rows equals height / cell size and self.columns equals width / cell size. This operator is the floor division operator in Python. Floor division divides the left-hand operand by the right-hand operand, rounding down to the nearest whole number to return an integer result. So both numbers will be ints. Let's also create an attribute to hold the cell size. Self.cellSize equals cell size. Now we are ready to create the grid. We will represent the two-dimensional grid of the simulation as a list of lists. This list of lists will be an attribute of the grid class. Let's call it cells. Self.cells equals 2. Now let's create this list of lists using list comprehension. Opening bracket, 0, 4, underscore, in range, parenthesis, self.columns, closing bracket, 4, underscore, in range, parenthesis, self.rows, and a closing bracket. This part of the code here creates a list filled with zeros, and this part of the code repeats that process. So with this line of code, we generate the grid and we fill all of its cells with 0. The init method of the grid class is ready. Now we create a draw method that will be responsible for drawing the grid on the simulation window. Def draw parenthesis self, window. This method will take the surface to draw on as an argument. To draw the grid, we will draw each cell of the grid. If the cell we have to draw is dead, we will draw a gray square. Else, if the cell is alive, we will draw a green square. Let's do it. We have to loop through all the cells of the grid. For row in range, parenthesis, self.rows, colon. For column in range, parenthesis, self.columns, colon. Now let's create a color variable to hold the color we want to use to draw the cell. Color equals to, parenthesis, 0, 255, 0 if self.cells, brackets, row, brackets, column. We have now created a green color and we assign it to the color variable if the cell is alive. We can continue this line of code by assigning a light gray color if the cell is dead. Else, parenthesis, 55, 55, 55. That's it. We can now draw every cell using the draw method of the Pygame library. First, let's import Pygame at the top of the file. Import Pygame. Now, inside the draw method, we will use the pygame.draw.rect function. Pygame.draw.rect, parenthesis, surface, color, parenthesis again, rect. We need to enter some info to this function. First, we need to enter the surface we want to draw on, window, then a color. We have the color in the color variable, color, and now we need a rectangle. This is a tuple of 4 values. The x and y coordinate of the top left corner of the rectangle and its width and height. The x coordinate is column times self.cell size, the y coordinate is row times self.cell size, and the width and the height of the rectangle, since we want to draw a square, is the same, self.cell size, self.cell size. Beautiful. Our first version of the grid class is ready. Let's test it at once to see if it works. Let's go to the main.py file and create a grid object. First of all, let's import the grid class. From grid, import grid. Now, outside of the game loop, we will create a grid object. We will give the constructor all the information it needs. Grid is equal to grid, parenthesis, window width, window height, cell size. We then need to call the draw method inside the game loop. Grid.draw, parenthesis, window. We need to pass in the display surface as an argument. Let's run the simulation now. As you can see, our window has become light gray. That's because all the cells in the grid are dead, so we give them a light gray color. But since there are no grid lines, we cannot see the cells. We just see a solid gray color. Let's go back to the grid class to make a small change. One way to create the grid lines is to make the squares we draw for the cells smaller. Let's make them 1 pixel smaller in width and height. So, in this line of code, here we define the size of the squares to be cell size. Let's make the width and the height of the square self.cell size -1, here and here. Perfect. Let's go back to the main.py file and run our program once more. Beautiful. As you can see, we now have a grid filled with dead cells, but we can see the grid lines. Let's now create an alive cell to see if our code works. So, outside of the game loop, let's alter the value of a single cell. Let's say the top left cell, grid.cells bracket 0 equals 1. And let's run the simulation. Perfect. The top left cell has now turned green. It is alive. Let's duplicate this line and let's test it with row 3 and column 2. Grid.cells brackets 2 brackets 1 equals 1. We start counting the rows and columns from 0. That's why we enter 2 and 1 for the row and column in the cells list. If we run the program again, we can see that another cell has become alive. Our grid class works as expected. We have successfully completed step number 3. Now we can start implementing the rules of our simulation. These rules are what breathe life into our simulation, transforming a static grid into a dynamic ecosystem. Game of Life is governed by 4 simple rules applied to each cell in the grid based on the state of its 8 neighboring cells. Here's a quick recap of the rules. Under population, a live cell with fewer than 2 live neighbors dies, as if by underpopulation. Stasis. A live cell with 2 or 3 live neighbors lives on to the next generation. Overpopulation. A live cell with more than 3 live neighbors dies, as if by overpopulation. Reproduction. A dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. Before working on the rules, let's work on the organization of our game to make our lives easier. So far, we have created a grid class to represent a 2-dimensional array of cells. Let's also create a simulation class that will be responsible for creating a grid object and apply the rules on the grid. By encapsulating the game logic within this class, we can maintain a clean and organized code base, making it easier to understand, debug, and potentially expand in the future. First of all, in the main.py file, let's delete the grid object we have created. It was for testing purposes only. So we have to delete the import of the grid class here, the creation of the object here, and the assignment of values to some cells, and lastly, the call to the draw method. Now we can start creating our simulation class. Ctrl+N to create a new file, and Ctrl+S to save it as simulation.py. Class simulation : def init parenthesis self. The simulation class will hold a grid. So let's import the grid class. From grid import grid. Self.grid is equal to grid parenthesis. But to construct a grid, we need some information. We need the width and the height of the simulation window and the cell size. So in the initializer of the class, we pass these information arguments: width, height, cell size. And now we can complete the creation of the grid. Self.grid is equal to grid parenthesis width, height, cell size. Now let's create a draw method that will draw the grid on the simulation window. Def draw parenthesis self, window, : Inside this method, we just have to call the draw method of the grid object. Self.grid.draw parenthesis window. Cool! Our first version of the simulation class is ready. Let's go back to the main.py file to test it out. First, let's import the simulation class. From simulation, import simulation. We can now create a simulation object. Simulation is equal to simulation parenthesis window width, window height, cell size. Lastly, we can call the draw method of the simulation object. Simulation.draw parenthesis window. If we run the program now, we can see the grid appears. Cool. We can now start implementing the rules of the simulation. For every cell on the grid, we need to find how many live neighbors that cell has. We will create a method for this in our simulation class. But before this, let's manually turn a cell on the grid alive to work with. Outside of the game loop, let's make cell brackets 3 brackets 4 alive. Simulation.grid.cells brackets 3 brackets 4 equals 1. Let's run the simulation. Cool, a cell is alive. We need a method to count how many cells around this cell are also alive. Let's go to the simulation class to create that method. At the end of the file, we add def count live neighbors parentheses self, grid, row, column, colon. This function will take 3 arguments, a grid, the row, and the column of a cell, and it will return how many of the neighboring cells are alive. The neighboring cells of a given cell in a grid, like the one at row 4 and column 5, can be identified based on their relative positions. Each cell has 8 neighbors, above, below, to the left, to the right, and the 4 diagonal directions. Let's break down the positions of these neighboring cells in terms of their row and column numbers, keeping in mind that we start counting rows and columns from 0. For the cell located at row 4, column 5, its neighbors' positions are determined as follows: directly above, row 3, column 5, directly below, row 5, column 5, to the left, row 4, column 4, to the right, row 4, column 6, diagonal upper left, row 3, column 4, diagonal upper right, row 3, column 6, diagonal lower left, row 5, column 4, diagonal lower right, row 5, column 6. To represent these positions programmatically, we can use a list of tuples, where each tuple contains the row and column offsets relative to the target cell. For example, the cell directly above will have offset values -1, 0, the directly below 1, 0, and so on. So we will have a list of the offsets of all the neighboring cells. Let's do it. In the count live neighbors, we first create a variable to hold the live neighbors. Live neighbors equals 0. Now we will create a list of tuples of the offset of all the neighboring cells. Neighboring offset is equal to brackets, and here are all the tuples we need. Now all we have to do is to iterate through this list of offsets and add each offset to the position of the live cell we are checking, and check if the new position is holding the value 1. For offset in neighbor offsets colon, if self.grid.cells brackets row plus offset brackets 0 brackets column plus offset brackets 1 equals 1 colon. If the new position holds the value 1, we have to increase the live neighbors variable, live neighbors plus equals 1. And finally, let's return the live neighbors variable, return live neighbors. Let's test this method in the main.py file. We have an alive cell. Let's create some more live cells around this cell to see if the count live neighbors method works as expected. Simulation.grid.cells brackets 3 brackets 5 equals 1. Simulation.grid.cells brackets 4 brackets 5 equals 1. And simulation.grid.cells brackets 2 brackets 5 equals 1. Now let's print to the console the value the count live neighbors method returns for the original alive cell. Print parentheses simulation dot count live neighbors parentheses simulation.grid, 3, 4. If we run the game now, we can see 4 live cells in total, and at the console the number 3 is printed. Cool, our method works, but we have a small problem. What happens if the live cell is at the border of the grid? Let me show you what I mean. Let's remove these live cells and create another one. Simulation.grid.cells brackets 5 brackets 29 equals 1. Let's also remove the print statement or the simulation will crash. If we run the game, we can see that this live cell is at the edge of the grid. How can we count the neighbors of this cell in this case? There are many ways to solve this. The way I prefer is to treat the grid as if it wraps around, creating a toroidal array. This means the right edge connects to the left edge, and the top edge connects to the bottom edge, creating a continuous surface. In this model, a cell on the right edge of the grid has neighbors on the left edge, and similarly for the top and bottom edges. So, in this example, our living cell will have these neighbors. Implementing this approach requires adjusting how we calculate the positions of neighboring cells. Instead of directly adding the offsets to the cell's position, we use modular arithmetic to ensure that the result wraps around the grid dimensions appropriately. Take a closer look at a cell positioned at row 6, column 30 in our grid. For a moment, consider that we want to identify its right-hand neighboring cell. You might think this neighbor is out of bounds, given our grid ends at column 30. However, due to the wraparound nature of our grid, the right neighbor effectively appears at the beginning of the same row, essentially at row 6, column 1. To mathematically resolve this and correctly calculate the neighbor's position, we apply an offset to move one step to the right. This places our hypothetical new cell position at row 6, column 31. Yet, since our grid doesn't have a column 31, we need to wrap this position around to the start of the row. This is where the modulo operator comes into play. The modulo operator returns the remainder of a division between two numbers. So, 31 modulo 30 simplifies to 1, because when you divide 31 by 30, the remainder is 1. Also, minus 1 modulo 30 results in 29. Therefore, by using modulo arithmetic for both row and column indices, we can ensure that any cell positioned beyond the last row or column, or before the first row or column, wraps around the opposite end of the grid. This maintains the seamless continuous space required for the game of life's logic. Let's do it. Let's go back to the simulation class and edit the countLiveNeighbors method. First of all, our method needs to know how many rows and columns our grid has in order to know if a cell is at the edge of the grid. The simulation class does not know this info. Let's calculate it. We will create two new attributes. Self.rows equals to height / cell size. Self.columns equals to width / cell size. Now we can use this information inside the countLiveNeighbors method. So inside the for loop here, we will add the following two lines of code. New row is equal to parenthesis row plus offset bracket 0 %, that's the modulo operator, self.rows. New column equals to parenthesis column plus offset brackets 1 % self.columns. Instead of just adding the offset row and column, we calculate the modulo of this value. Now we can edit the next line of code like this. If self.grid.cells brackets new row brackets new column equals 1 colon. That's it, our method is ready. Let's test it out. Let's go back to the main.py file. Let's add 3 new neighbors to the live cell at the other end of the screen. Simulation.grid.cells brackets 6 brackets 0 equals 1 and simulation.grid.cells brackets 5 brackets 0 equals 1 and simulation.grid.cells brackets 4 brackets 0 equals 1. And let's print its living neighbors. Print parenthesis simulation.countLiveNeighbors parenthesis simulation.grid, 5, 29. Perfect. As you can see in the console, we get the value 3. Our method works fine. Cool. Another step is now complete. And believe it or not, we are just a few minutes away from running our simulation for the first time. Well done on reaching this far in the tutorial. The next step is to implement the rules of the simulation. Let's take another look at the rules. There are 4 rules to the game, as we saw earlier. But if we look closely at the rules, we can reduce the logic of the rules to just two. Rule 1. If a cell is alive, it dies when it has fewer than 2 or more than 3 live neighbors, else it stays alive. Rule number 2. If a cell is dead, it can become alive only if it has exactly 3 live neighbors, else it stays dead. Now let's implement those two simple rules. First of all, let's delete the alive cells we have created in the main.py file and the print statement. Now let's go to the simulation class and create an update method. This method will be responsible for updating the simulation state according to the rules. Dev update parenthesis self colon. Now here is the tricky part. We need to loop through the cells of the grid and apply the rules of the simulation at the current state of the grid. If a cell must be changed from dead to alive, we can't save it to the grid because this will alter the state of the grid and this will affect its neighboring cell's state as well. We want to change all the cell state at once, but we can't do that either. So here is what we are going to do. We are going to create another grid, a temporary grid, where we will save all the changes we make to the original grid after implementing the rules to the original grid. Then we will copy all the values from the temporary grid to the original grid and we will display the original grid. I understand that this method might not be the fastest one to execute on a computer, but this is the easiest way to achieve what we want. I will prepare a detailed video on ways to make the simulation run faster in the future, if you are interested. So, in the class initializer, let's create another grid. Let's duplicate this line of code. Ctrl plus Shift plus D to duplicate this line. Now we can change the name of the second grid to temp grid. Now, in the update method, as we said, we need to check every cell of the grid. That's a nested for loop. For row in range parenthesis self.rows column. For column in range parenthesis self.columns colon. Now for every cell we need to count its neighbors. Live neighbors is equal to self.count live neighbors parenthesis self.grid row column. Now let's get the value the cell contains. It's either 1 or 0. Cell value is equal to self.grid.cells brackets row brackets column. Perfect. Now we can implement the first rule. If cell value equals 1 colon. If live neighbors greater than 3 or live neighbors less than 2 colon. Now the cell must die, but we will set the new value to the temporary grid. Self.tempGrid.cells brackets row brackets column equals 0 else colon self.tempGrid.cells brackets row brackets column equals 1. That's it. The first rule is ready. Be careful. We need the else statement here as well. Don't omit it. We need to update the value of every cell of the temporary grid. Now we can implement the second rule. Else colon. If live neighbors equals 3 colon self.tempGrid.cells brackets row brackets column equals 1 else colon self.tempGrid.cells brackets row brackets column equals 0. Perfect. We now just need to copy all the values from the temporary grid to the original grid. We will use a nested for loop to achieve that. For row in range parenthesis self.rows colon. For column in range parenthesis self.columns colon. Self.grid.cells brackets row brackets column equals to self.tempGrid.cells brackets row brackets column. Perfect. Believe it or not, the logic of our simulation is ready. It is just 20 lines of code. We are ready to test it out. But our grid is currently empty. Let's create a method that will assign random values to the cells of the grid. Let's create that method in the grid class. We open the grid.py file one more time. We type def fill random parenthesis self colon. Again, we need to loop through all the cells of the grid. For row in range parenthesis self dot rows colon. For column in range parenthesis self dot columns colon. Now we give this cell a value, either 0 or 1. For this, we are going to use the random module, so we need to import it, comma random here. Now we will use the choice function, which returns a random element from a list. Self.cells brackets row brackets column equals to random.choice parenthesis brackets 1, 0. This line of code will fill the grid with random values, with approximately half of the cells being zeros and the other half ones. If we want the grid to have more zeros than ones, we can create a list to choose from with more zeros than ones, like this. Brackets 1, 0, 0, 0. Now, 25% of the cells will be alive and 75% of them will be dead. Cool. Now, let's go back to the simulation class and call this method in the initializer method of the class. Self.grid.fillRandom parenthesis. We are ready. Let's go to the main.py file and call the update method of the simulation class inside the loop, in the part where we update the simulation. Simulation.update. We can now run our program again. Amazing stuff. Our simulation is alive. The simulation is running at 12 frames per second, and you can see the complex and mesmerizing patterns that arise from the two simple rules we have implemented. I really find it fascinating. I have spent many hours just looking at the lifelike patterns that emerge from time to time. It is so cool. The way we structured our code, it is very easy to create bigger or smaller grids. We can change the dimensions of the simulation window and the cell size to make a much bigger simulation, for example. Let's say window width is 1200 and window height is 800 and cell size is 4. That's 75,000 cells. If we run the simulation, we can see it works. Amazing stuff. With this bigger resolution, we can appreciate the beauty of the game of life algorithm even better. Check out some fantastic patterns that emerge, like this one. I can't stop staring at it. Now let's close the simulation and change the dimensions again to the ones we had before. With this, another step is complete. Our simulation is working fine, but we can add some cool features to it to make it even more fun. Let's give the user the option to start and stop the simulation by pressing certain keys on his keyboard. To achieve this, let's go to the simulation.py file and add a new attribute to it. Let's call it run. Self.run equals false. Now let's create a method that will tell us if the simulation is running or not. Let's create it here. Def is underscore running parenthesis self colon. Return self.run. This method just returns the value of the run attribute we just created. We can use this method inside the update method. We want to update the state of the simulation only if the simulation is running. If self is running parenthesis and colon. Now we select all the code of the method and we indent it with a tab. Perfect. Next, let's create two more methods to start and stop the simulation. Let's create them right here. Def start parenthesis self colon. Self.run equals true and def stop parenthesis self colon. Self.run equals false. We can now go to the main.py file. We want to start the simulation when the user presses the enter key on the keyboard and to stop it when the user presses the spacebar key. First of all, we have to know when the user presses a key on his keyboard. Each time a key is pressed on the keyboard, a pygame event occurs. We can detect that event. So, inside the game loop, where we check for events and process them, we add this code. If event.type equals pygame.type key down, colon. This line of code checks if the event type is equal to the key down constant, which means the player has pressed a key. Now we have to know which key the player pressed. We have a constant for each key in the keyboard. To know which key the player pressed, we can use the event.key attribute. The event.key attribute returns a constant representing a key that was pressed. Now we can check if the player pressed the enter key. We can do that with this if statement. If event.key equals pygame.k return colon. If the player presses the enter key, we have to start the simulation. Simulation.start. Let's also alter the caption of the simulation window to know the state of the simulation. Pygame.display.setCaption parenthesis quotes. Game of life is running. Now we need to stop the simulation if the user has pressed the spacebar on the keyboard. Elif event.key equals pygame.k underscore space colon simulation.stop and pygame.display.setCaption parenthesis quotes game of life has stopped. Perfect. Let's test the simulation. As you can see, now when the simulation starts, it is not running, but displays the dead and alive cells. If we press the enter key, the simulation starts running. And if we press the spacebar, the simulation stops. Very cool. But what if we want to speed up the simulation or slow it down? We can manually change the FPS variable and run the simulation again. Another way is to use the keyboard to control the simulation speed. Pressing the F key will make the simulation go faster, and pressing the S key will slow it down. So we add a couple more if statements here. Elif event.key equals pygame.k underscore f colon fps plus equals 2. If the user presses the F key on the keyboard, we increase the maximum FPS limit by 2. Else, if the user presses the S key on the keyboard, elif event.key equals pygame.k underscore s colon if FPS greater than 5 colon FPS minus equals 2. We decrease the max FPS value by 2 if the FPS is greater than 5. I don't want to decrease it any further because the simulation window becomes less responsive. Let's run the simulation one more time. Perfect. Now we can start and stop the simulation and we can make it go faster or slower. Very cool. Another step is now complete. Now the last thing I want to add to this project is the ability for the user to edit the grid manually by clicking on the cell to create his own simulation. When the program starts, the grid must be empty and the user will have the option either to create his own simulation or a random one. So let's go back to the simulation class. When the program starts, we need an empty grid. So let's remove this line of code where it fills the grid with random values. Now let's go to the grid class and create a new method that will clear a grid. Def clear parenthesis self colon. For row in range parenthesis self.rows colon. For column in range parenthesis self.columns colon self.cells brackets row brackets column equals 0. We loop through the cells of the grid and we clear them by setting their value to 0. Now we can go back to the simulation class and create a new method called clear that is going to clear the grid if the simulation is not running. Def clear parenthesis self colon. If self.is running equals false colon self.grid.clear. We clear the grid attribute in this method only if the simulation is stopped. Now let's also create a new method that will fill the grid with random values if the simulation is stopped. Def create random state parenthesis self colon. If self.is running equals false colon self.grid.fill random. Now let's go back to the main.py file. If we run the program now, we can see the program starts with an empty grid. So let's give our program the option to create a random grid by pressing the R key on the keyboard and to clear a grid by pressing the C key on the keyboard. So, in the loop, where we check for key events, we add two more if statements. elif event.key equals pygame.k_r simulation.create random state. Now we can add another if statement to clear the grid when the user presses the C key. elif event.key equals pygame.k_c simulation.clear. Let's test it out. As you can see, the program starts with a blank grid. When I press the R key on the keyboard, the grid is filled with alive cells at random. If we press Enter, the simulation starts running, and if I press the spacebar, the simulation stops. I can now press the C key on the keyboard and all the cells are cleared. Very cool. The last thing we have to implement is manually editing the grid by clicking on the cells with the mouse. This feature will allow users to customize their starting grid before running the simulation, adding another layer of interactivity to the program. Luckily, that's very easy to implement. There is another type of event in Pygame, the mouse button event. This event is triggered each time the user presses any key on the mouse. Let's use it. We add another if statement in the event loop here. I will put it here, just under the quit event code, to be clear that this is a Pygame event type and not a key down event. elif event.type equals pygame.mouse button down : Next, we need to retrieve the current position of the mouse cursor. There is a Pygame function for this. Pause is equal to pygame.mouse.getPose. When this line of code is executed, pygame.mouse.getPose returns a tuple containing two integers, representing the mouse cursor's x and y coordinates on the screen. The x-coordinate indicates the horizontal position of the cursor, while the y-coordinate specifies the vertical position. We can use this info to calculate over which cell the cursor is located. Row is equal to pose brackets 1 // cell size, and column equals to pose bracket 0 / cell size. Now all we have to do is to simply change the value of that cell. Now it is tempting to just add a single line of code here and alter the value of the cells of the grid attribute of the simulation object, but it is not a good programming practice. Instead, what we are going to do is to go to the grid class and add a new method to it. We will call it toggle cell. If the value of the cell is 0, it will change it to 1, and if it is 1, it will change it to 0. Def toggle cell parenthesis self, row, column, self.cells brackets row brackets column equals to not self.cells brackets row brackets column. It is also a good idea to add a check if we are given invalid row and column values. If 0 less than or equal to row, less than self.rows, and 0 less than or equal to column, and less than self.columns, and now we indent this line of code. Our method is ready. We can now go to the simulation class and add a new toggle cell method here. Def toggle cell parenthesis self, row, column. We can limit the usage of this function only when the simulation is not running. If self.is running equals false, self.grid.toggle cell parenthesis row, column. Perfect. Now all we have to do to complete our project is to go to the main.py file and call this new method. In the loop here, we just type simulation.toggle cell parenthesis row, column. Let's test our code one more time. Now each time I click on a dead cell, it turns alive, and if I click on an alive cell, it dies. Very cool. With this feature, we can now start playing with some game of life patterns. Check this out. This pattern is called a glider. If I press enter to start the simulation, the glider starts moving on the screen. How cool is that? Since the grid is unlimited in size, because we wrap around the edges, the glider will live forever. Let me show you another cool pattern. If I create a much bigger grid and create this pattern, then let it run for a few seconds, you can see it is a pattern that creates gliders. Amazing stuff! In other words, there are patterns in these simulations that, combined, can create incredible stuff. Some users have created logic gates inside the game of life with patterns like the ones that I showed you. Some others combined these logic gates and created a CPU inside the game of life. And some very bright individual even created the game of life inside the game of life simulation. This is why I love computers and programming. With just 200 lines of code, we created something so complex and endlessly fascinating. This illustrates the beauty and power of programming, how simple rules and concepts can evolve into complex systems and behaviors. The game of life, despite its straightforward setup, serves as a profound example of emergent behavior, where complexity arises from simplicity. It's a perfect demonstration of how programming can mimic natural processes and even lead to self-replicating structures, much like life itself. Before we wrap up, I'd like to highlight that the project's code has been designed with clarity and ease of understanding in mind, rather than optimizing for performance. This approach ensures that the concepts and logic behind the project are accessible to everyone, especially those new to programming or the game of life simulation. I plan to create a new video tutorial dedicated to optimizing the code for performance. If it is ready, it will appear here. If it is not ready yet, check out some of my other tutorial videos and be sure to subscribe to my channel in order to be notified when I release a new video. Thank you very much for watching. I'll see you next time.